Hello, in this video I'm going to teach you 5 different types of chemical reactions and how to identify them. So the first type is called a synthesis reaction, and at the molecular level, this happens when you have a couple different chemicals that fuse together. They synthesize a bigger chemical. Now the second type is the opposite of synthesis. It's called decomposition, and it happens when you have one very big chemical that breaks into pieces. It decomposes. That's what it means to be broken apart like this. Now we have a single replacement reaction, which is what happens when you have a compound and an individual element, and the compound actually gets ripped apart, and part of it moves over to join the other element. So, in a single replacement, this moves over, this guy gets replaced, and then ends up single and lonely at the end. Single replacement. A double replacement is similar but a little bit different. You have 2 different compounds, and the compounds switch partners. The difference is that in a single replacement, everybody at the end is not paired up. In a single replacement, this person is going to be alone and single. But in a double replacement, everybody has a partner at the end. Finally, there is combustion. Combustion reactions make fire, but chemically there's not very much super interesting happening. You have some kind of fuel combining with oxygen to form carbon dioxide and water. You might wonder where the fire is right here, but the fire isn't actually a chemical. The fire is a process. This arrow represents the fire that you would see in a combustion reaction. So it has to have oxygen in the reactants and carbon dioxide and water in the products. Now, knowing conceptually is one thing, but being able to identify from a reaction is another. To identify the type of reaction that's being represented, you need to look at the reactants and the products, which are the things before and after the arrow. You can basically ignore the coefficients or the numbers in front. These are useful when we're balancing, but not so much when we're categorizing. So, a synthesis reaction has many different reactants, but only a few different products. The number goes down because they combine. For example, in this case you have hydrogen and oxygen. That's 2 different reactants, but only one product, water. So because I have 2 reactants, but one product, it's a synthesis reaction. And these, ignore the coefficients, they don't matter right now. Here's another one. Notice once again that I have 2 reactants, but only one product. Synthesis, they're combining. Last one, I have 2 reactants and 1 product. Synthesis, they're combining. I could add more than 2, 3 or 4. Doesn't matter though. As long as you have more reactants than products, you're synthesizing, building them up to make bigger parts. Decomposition is the opposite, so instead of having more reactants than products, in this case you have more products than reactants. Because you have one big chemical, in this case it's a water molecule, and it splits into 2. Hydrogen and oxygen. So I have 1 reactant and 2 products. That's how you know it's decomposition. It's breaking down. In this case I have a big aluminum oxide that breaks into pieces. The aluminum goes that way, the oxygen goes that way, basically. Now, single replacement is a little bit different. Decomposition is easy because I have more products than reactants, and synthesis I have more reactants than products, but single replacement, I'm going to have 2 different reactants and 2 different products. You can tell it's a single replacement reaction though, because you look at a chemical made of 2 different parts. Right here I have copper and chloride. Then just one element, or a polyatomic ion. In this case it's just zinc, lonely. And then the reactants, or the products you get, are the 2 chemicals that you would get by switching that single element. Now what I mean by that is, this zinc has to switch with the copper. And that's what I get. I get zinc chloride instead of copper chloride. And this copper ends up alone by themselves. That's why it's a single replacement. Here's another one. I have an aluminum chloride and a magnesium. You can see this magnesium is going to kick out the aluminum and become magnesium chloride, whereas the aluminum is by itself all alone. This one is a little bit weird because you have the calcium, and the calcium kicks out the hydrogen to become calcium chloride, but at the end it seems like I have H2. Now where did this come from? Because you would expect if this one hydrogen got kicked out, it would just be an H. So why is it H2? Now, some elements, bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine, they're unstable unless they're in pairs. So this right here, you can act like this is single and not paired up, because it used to be single. That seems weird. Let me show you what I mean. I have this calcium and 2 hydrogen chlorides. This is what they look like. Now, a single replacement reaction is going to happen. What's going to happen is these guys are going to be left single, the hydrogens, because the calcium is going to steal the chlorines. Now I have these 2 single hydrogens. But because hydrogens are diatomic, they're one of those unstable ones, they pair up to form H2. later, after the replacement reaction happens. So this is kind of another thing that gets made as like a secondary reaction, but don't worry very much about it. Just know that if you have this counts as just one single element. It's not a compound. So if you have any single elements involved, it's a single replacement. Double replacement reactions you can identify because I have one chemical made of different elements, so a compound, another chemical made of different elements, so two compounds, and my products are the chemicals you would get by swapping the parts. So I have a compound and a compound, making a compound and a compound, and you get this by swapping the hydrogen and the sodium. That's how you get the products. In this case, everything is a compound. There are no pure elements. Right, I have sodium, oxygen, hydrogen, hydrogen, chlorine, sodium, chlorine, hydrogen, oxygen. None of these are pure elements. They're all compounds. And you can see that the sodium and the hydrogen swap places. That's how I get this stuff. Finally, this one looks very complicated, but all you have to see is that I have all these compounds that are not combining. The beryllium and the rubidium switch places. These things with the numbers after the polyatomic stuff, you can basically ignore them. Just look at what happens to the first easily identifiable atoms. If they swap, it's a double replacement. And finally, combustion is very easy. Everything is exactly the same except for the fuel. That can be different. So you have fuel combining with oxygen to form carbon dioxide and water. This is combustion. That's the fuel. This is combustion. That's the fuel. This is methane. That's octane. But every other part of the reaction has to be exactly the same. Here's a quick chart. For simple reactions, if you have more reactants than products, you're synthesis. Because you start with a lot of things, but you turn them into only one. So more reactants than products, synthesis. If it's the opposite, you have more products than reactants, it's decomposition, because you have one big chemical, and it splits into a couple different other chemicals. So decomposition if you have more products than reactants. Now, if you have the same number of products and reactants, it's going to be one of the replacements. So that means that if I start with two things, and I end with two things, it'll be a single or double replacement. You got to check to see if there are any pure elements that get left alone, in which case it's single replacement, because the pure elements are single and lonely, or if everything is a compound, in which case it's a double replacement, because things switched places, they didn't get kicked out. And then finally, for combustion, it has to be exactly this reaction. Some type of fuel mixes with oxygen gas to form carbon dioxide and water. So combustion is one that you might just have to memorize. Let's practice a little bit. What kind of reaction is this? I'll give you 5 seconds. 4, 3, 2, 1. Well, notice that I have one thing right here, and it splits into two different products. So one splitting into two is going to be decomposition. It breaks down. What about this? I'll give you 5 seconds. 4, 3, 2, 1. Okay, well this one is going to be a single replacement. What's going to happen is the oxygen and the chlorine are going to switch places, like that. Well, the oxygen is going to kick out the chlorine, and the chlorine is going to be alone. You know it's a single replacement, not a double replacement, because this right here is a pure chemical. It's only made of chlorine, and this is a pure chemical. It's only made of oxygen. So these two things are not compounds, and so it can't be a double replacement. It's got to be a single replacement. Because O2 is just made of oxygen, it's pure. Cl2 is just made of chlorine, it's pure. And double replacements don't have any pure things, they only have compounds. What about this one? 5, 4, 3, 2, 1. Well, this is going to be a synthesis reaction, and you can tell because I have two different chemicals that I combine into one bigger chemical, so combining is synthesizing. What about this one? 5, 4, 3, 2, 1. Well, so first thing you got to notice is that I have two reactants and two products, right? I have two things turning into two things. And that means it can't be synthesis or decomposition, because these both involve combining things or breaking them. So it's going to be combustion, but it's not combustion because I don't see any oxygen, carbon dioxide, and water, so it's not combustion. It's got to be one of the replacement reactions, right? If you have the same number before and after, it's a replacement reaction. And you can tell that it's not a single replacement because I have no pure things involved here, right? This is a compound, that's a compound, that's a compound, that's a compound. So just based off of that, you can tell it's double replacement. Or you could try to literally picture what's happening in your head, and you can see, oh, well right here the lithium was stuck to the carbonate, right? And right here the magnesium was stuck to the chlorine, but over here the lithium is stuck to the chlorine. So what must happen was this must take that place, and then the magnesium must take that place. So they must have swapped. And if you swap, you get a double replacement reaction. Finally, this one you might just have to memorize, but the fact that I have something plus oxygen making carbon dioxide and water makes it combustion. I hope that was helpful. You should be able to identify, based off of these things, what kind of reaction it is, like from this bank. And then you should also be able to conceptually understand what happens when, for example, chemical splits. So like when two chemicals swap, what is that? Double replacement. If you got that, you got everything. Hope this is helpful.